The derivative of a function gives the rate of change of that function, which could also be changing, which means that we can take the derivative once again. So here's an example. I got distance over time. That's the first derivative, which would be an example of velocity. But the velocity could be changing over time. When I take its derivative, that's the second derivative, which gives me the acceleration. But the acceleration could also be changing over time. That's the third derivative, which is called the jerk. That's what we were experiencing with that car crash on the opening image there. But the jerk could also be changing over time. That's a fourth derivative. That's an example of something called a jounce. So what we're concerning ourselves with right now, velocity is the instantaneous rate of change in the position function. It's change in distance over change in time. I'm getting the derivative of the position function. It's going to give me the velocity. But the velocity could be changing over time. And if it's changing over time, we're finding the acceleration. It's the instantaneous rate of change in the velocity function. So I tend to think of this in terms of a ladder here. And here you've got this woman who's probably bird watching. Yeah, she's probably bird watching. And so I'm going to start with, at the top of my ladder here, the position function. To move down the ladder here, I'm going to take the derivative of that position function in order to find the velocity. And then I can take the derivative again, moving down this ladder, to find the acceleration. So it's differentiation that's going to take me down the ladder. We will learn in the future that if I want to go back up this ladder, it's going to be the inverse operation of differentiation, which is integration. So over here in the margin, as a recap, S of t is our position equation. If we take the first derivative, we're going to get the velocity function. If we take the second derivative of the position equation, which is the first derivative of the velocity equation, we're going to get the acceleration function. So let me show you some notations for higher order derivatives. In terms of the little prime marks, the Lagrange, all you have to do is just keep adding little tick marks. Right? First derivative, second derivative, third derivative, but everything after that, notice that in parentheses it gets a 4. It's different from an exponent, of course, have to distinguish it in some kind of way, so it gets little parentheses. And so a fifth derivative will have a little 5 in there, so there's the generic nth derivative. You can see it in terms of y's. You can also see it in terms of your function named f. Okay, the Leibniz notation, the way it works is a little bit different. Here's our first derivative. Look at the second derivative. On the second derivative, d2 over dx2. Why is that? Why is the 2 on the d on the top and the 2 on the x on the bottom? Well, look over here in the margin. Remember that we are taking the derivative with respect to x of dy dx. And now if you think of it as fractions like that, that's where this notation is coming from. You have this d squared, over dx dx, it's like dx squared. And that's the reason for that particular notation, and you can see it plays out with a third derivative, a fourth derivative, and so on. And here you can see it in terms of some generic function f of x. And then the last column there is the Euler notation, where that d means take the derivative with respect to x of some function inside here. You want the second derivative? Just put a superscript with a 2, a third derivative, a fourth derivative, and so on. All right, so back over here in the margin, we've got the derivative with respect to x of the derivative of y with respect to x, that's the first derivative, is going to give us this second derivative.